chapter 7, the only things, we haven't talked about like 2 or like little details, like minor things I could have added in yesterday, but I just continued on here. So, correlation does not necessarily indicate that one variable causes the other. In fact, in this class, we will never prove that anything causes anything. Okay? So when we're looking at one particular data set, that is one moment in time and that is one data set, just one data set is not enough to prove something. Okay? Also, there can be a correlation between two variables, but there could be something else happening in the background. For example, the book uses this. They plot the number of storks nesting in some country and then the number of births during that same season. And there's a strong positive correlation, but that does not mean that because there were more storks that there were more babies, because we all know that storks really don't bring babies. So
yeah. You've never heard of storks bringing babies? You've never heard that?
There you go.
I thought it was like stork babies.
No, like actual human babies, not stork babies. So make sure you don't just say, like, it's going to ask you all in the homework tonight, it's going to say, does this prove this? Does this prove? We don't, I can tell you, we don't prove anything in this class. We are very wishy-washy in here, okay? We can say that there's a correlation, we can say there's an association or relationship, but we never prove anything. Proving something takes a lot more than one data set. The book uses another great example, okay, that the U.S. Surgeon General took forever to be able to get warning labels on cigarettes because they were trying to link cigarette use to lung cancer, and they had lots and lots of evidence, and it took a long time to get enough evidence to actually prove there was a link between the two. Okay, so we can't just prove something because they look at one scatter plot one time. It's just not going to work. Not going to do it. The last thing we need to talk about here is a lurking variable, and that's something going on in the background that may have caused that correlation. So, for example, one of the ones in the book yesterday was elementary school age weights, like kids' weights, and then their reading score. And you guys all said there was no association, but I said if you looked at the scatter plot, that the more they weighed, the higher their reading score might get. It wasn't because of their weight, though. But that's what the two variables were in the scatter plot, right? You had weight and you had reading score. That's all you were looking at. But it was increasing not because of weight or reading score. It was increasing because of their age. Okay? So age was not actually one of the variables in the scatter plot. So we call that a lurking variable. It's something going on in the background that's actually causing the correlation. Okay? So that's why we can't just say, we're not going to say that weight causes a better reading score. Right? That's not what's actually happening. Probably age is what's leading to the higher reading score because they're getting older and they're learning more. Okay? So be aware of those things. Any questions about that? Again, down here, keyword, we never prove anything here. Ever. We have evidence that suggests things, but we never prove that anything happens. Okay. We also can talk about correlation tables. In a correlation table, you just have multiple variables. So maybe you measured multiple things. And so here they have a bunch of stuff about a company. And so you can do the correlation between multiple variables all in one table. So I can see the correlation between assets and sales, assets and market value, assets and profit. I can see all of them in one place instead of having to look at like a million different scatter plots. All right. Notice that the diagonals are all 1. Why is that? Why are those all 1?
Because if it's by the same thing, then it's
right, it's the same variable. It's like assets by assets. It's the same exact numbers. So you're going to have a perfectly straight line because it's the same numbers. It's like having the equation y equals x. Right? So those don't really count for anything. They're in the table because it's part of the table, but those aren't really relevant. They might ask you questions like, what 2 variables show the strongest correlation? The greatest correlation. So which 2 variables show the strongest correlation? Those don't really count. The ones don't really count. They're not really. No. Market value and profit. No. That's what Profits and cash flow, right? Because that's the greatest one. So when you're reading this, you said profits and market value. You were close. So when you're reading this, you're just looking at two different variables, but you're looking at a lot of them at the same time. That's all it is. It's nothing really that fancy. All right. Questions about what a correlation table is. Just holds a bunch of different correlations in it. All right. And the last thing are things that could go wrong. Don't say correlation when you mean association. That was in the homework last night. But keep that in mind, because I know that it's easy to just interchange those. I do it all the time by accident. Okay, so don't write those down. Don't correlate categorical variables, and you might say, how would they do that anyway? It's very easy for someone to take categories and assign numerical values to them. Like they're going to be like eye color. Well, blue eyes is going to be 1s, and brown eyes is going to be 2s. So then you have actual numbers, so then you could find a quote-unquote correlation, but it's still just a category, so it doesn't mean anything. Okay? Don't confuse correlation with causation. Again, we don't prove anything in this class. We don't say that one variable causes the other. We just have evidence of a relationship. Make sure the association is linear if you're going to use the correlation. That's important. Don't assume the relationship is linear just because the correlation coefficient is high. So if they give you R, but you don't have a scatter plot, don't assume that it is linear, because you can calculate R with whatever you want. And then beware of outliers, because that will definitely affect the correlation. For example, if I draw a scatter plot. All right, that's a fairly strong linear relationship, right? Positive. So let's say that R is, I'm making something up. We're going to say 0.8. It's probably stronger than that. We're going to say 0.8. What if I added in a point down here? Is the relationship stronger or weaker now? Weaker, so the correlation is going to decrease. Okay, so just be careful about that. Questions about those things? All right. So that ends what we need to talk about in Chapter 7.